Let's look at the idea of tangent lines to polar curves. We know that r is going to be a function of theta in polar curves, and we also know that x is equivalent to r cosine theta if we know r and theta, and y is equal to r sine theta from how we developed the relationship between polar and Cartesian form. So we can think of it as if they were in parametrized form. In other words, x is parametrized and y is parametrized, but it depends on r and theta. So we can say dy dx as before with parametric equations is dy d theta over dx d theta, but keeping in mind that this r that we deal with is actually a function of theta. So when I differentiate each piece with respect to theta, I have to think of it as a product and apply the product rule. So let's look at dy d theta, derivative of the first with respect to theta, dr d theta times the second, plus the first guy, r, as a function of theta times the second guy. The second guy is derivative actually. Derivative of sine theta is cosine theta. All over, same thing for the denominator. Derivative of the first with respect to theta times the second, plus the first guy r times derivative of the second, which is minus sine theta. So minus r and then sine theta. So this is actually, you can think of it as the slope of the tangent line that we used to call with parametric form. This is the slope of the tangent line for some theta. So if I know theta, then I can figure out at that theta what my slope of the tangent line is, of course, provided that I figure out what r is too. So instead of memorizing this, you can always remember that r will be given to you as a function of theta, and if you just simply plug it in, you can find your dy d theta and dx d theta just by applying the product rule right there and then and not having to memorize this formula. Let's look at an example. For the curve r equals 6 sine theta, find the slope of the tangent line at the angle pi over 2. So we'll just go apply this idea, get the slope of the tangent line, and then go look at the curve and see if things actually make sense. So I know again x is equal to r cos theta and y is equal to r sine theta. And instead of memorizing this formula, I will just know that r is given to me to be 6 sine theta. So I can go plug the guy in. So r is 6 sine theta times the cosine theta that's already there. And r is 6 sine theta times sine theta. So I guess 6 sine squared theta. Now everybody's already in terms of thetas, and I don't have to worry about r's because when I evaluate it, I'm given a theta, I just plug in the theta. So this is perfectly fine. You can leave it as is, and you can apply the product rule for differentiating this with respect to theta, but I notice that I can write that as 3 times 2 sine theta cosine theta. So I'm going to choose to use a double angle identity. Again, we do not have to do this. We can just leave it the way it is and find the derivative using the product rule. I'm going to write that as this guy is going to be sine 2 theta, because if I only have one function to deal with, it'll make it easier to differentiate with respect to theta. So now I can go find my dy dx as dy d theta over dx d theta, and everybody's already in terms of theta, so I'm good to go. So the derivative of this guy, remember this is sine theta, everybody's squared. Derivative of this guy with respect to theta, so 6 times 2 sine theta to the 1 times the chain rule derivative of the inside is cosine theta. And then the derivative of the x piece with respect to theta, so that's 3 times sine 2 theta goes to cosine 2 theta times the derivative of the inside times 2. So I'm going to end up with, it looks like another 2 sine theta cosine theta. I can use the same identity I used there. Again, I do not have to. I can just leave them as sines and cosines. So I have 6 sine of 2 theta over 3 times 2 is 6 cosine of 2 theta. So it looks like I have, I guess, tangent of 2 theta if I want to write it like that. So dy dx is tangent of 2 theta. I'm going to be evaluating this guy at theta equals pi over 2. And again, if you did not use any double angle identities, you would just do product rules, and at the end you'd have a bunch of sines and cosines, and you would plug in your pi over 2 into the sines and cosines, no big deal. So dy dx, or as we call it, m sub tan for us, at that angle ends up being tan of 2 times pi over 2, which is just tan of pi, which I guess is finally 0. So if all I needed was the slope of the tangent line, it looks like it's 0, which means it must be horizontal at that place. Now, let's go look at the graph actually. We should already know that that's a circle along the y-axis with a radius of 3, but we'll go put it in because it fits the form we talked about. Oops. So 6 sine theta. Let's look at the graph, and I'm going to have to go zoom out. Go to a standard zoom. So we do get that circle, and what we just concluded that at pi over 2, the tangent line, I guess, is horizontal because the slope is 0. So we know that that's pi over 2, and at pi over 2 it looks like the tangent line is horizontal, the slope is 0. If I needed the r value there too, I could just plug in the theta here. So if I plug in pi over 2, I get 1, which means r is 6. So the point I'm looking at in polar form is really theta, r theta. R is 6, and my theta is pi over 2. Again, if I plug in my pi over 2 into my original curve, I get an r value of 6. So as I'm sweeping through and going to pi over 2, the r value is 6. And right there, the tangent line is indeed horizontal. So if I needed, let's say, the equation of the tangent line, that would be easy. It's just a horizontal line going through the y value 6, so it would just be y equals 6 from what we saw on the TI also. So it confirms that the tangent line is horizontal. Let's go look at another example. So for this curve r equals 4 cos 2 theta, we want to find the slope of the tangent line at theta equals pi over 4, and then also find the equation of the tangent line there as well. We can look at the graph to get an idea of what it looks like, but let's go do the math and then see if things make sense or not. So again, x is equal to r cos theta, and y is r sine theta, and we know our r is given, so we just go plug them in. That way we can have everybody in terms of thetas. So 4 cos 2 theta, cos theta, leave that as is, and it looks like I'm going to have to apply a product rule. I have 4 cos 2 theta and sine theta. So I'm going to be applying the product rule when I find my dy dx. So dy dx is dy d theta over dx d theta, and we're going to end up with, maybe I'll just pull out the 4 and do the product rule with these two pieces. So I pulled out the 4, derivative of the first, negative 2 sine 2 theta times the second, plus the first times the derivative of this guy, which is cos theta. So let me fix that because I have that wrong. So first guy times the derivative of this, which is cos theta, over, let's pull out the 4 and do the same thing for dx d theta. So derivative of the first, negative 2 cos, or negative 2 sine 2 theta, times the second, which is cos theta, and then the first guy, cos 2 theta, times the derivative of this guy, which is minus, I'm looking over here, minus sine theta. So Simplify that or not, I have it at pi over 4. I can go, I guess these guys are done, it's a little tedious. This is evaluated at pi over 4, so it might be quick to just go put in pi over 4 in all of these and see what happens. Okay, so I plug those all in. Remember when I put pi over 4 in here, 2 times pi over 4 is actually pi over 2. So let's see what happens. Cosine of pi over 2 is 0, so that whole thing is gone, and cosine of pi over 2 is 0, so that whole thing is gone. Sine of pi over 2 is 1, so that makes it easy. And then sine of pi over 4, I guess, is root 2 over 2, and same thing here. Cosine of pi over 4 is root 2 over 2. So I guess ultimately we got the same guy at top and bottom, so we end up with a slope of 1. So let's go look at the graph and see if this makes sense. So let me graph. I put that into my R, and there is, it looks like a rose curve for cos 2 theta, and we said n is even 2, so it has 4 petals. And at pi over 4, which is right about there, it looks like the slope there we're finding is 1. So I guess it goes, let's see what we have, what point we have at pi over 4. Let's go analyze what R will be at pi over 4 also. It looks like R is equal to 0 at pi over 4. So it goes into the polar, into the origin with that angle, meaning x and y values are also 0. So since x is r cos theta and y is r sine theta, r is 0. So if you plugged it in there with the theta being pi over 4 or here, doesn't matter. It looks like both x coordinate is 0 and y coordinate is 0. So again, even if you just want your x and y coordinate right off the bat and you want to put theta in here, pi over 4, you will get 0 values, but it looks like r is 0 as we go into pi over 4. So the point is 0, 0, and the slope is 1, meaning as I'm looking at this curve at pi over 4, the r value is 0, so it goes, the piece of the curve goes into the polar, into the origin at an angle of pi over 4, and it goes in with a slope of positive 1, which kind of looks like, it does look like it could be a positive 1 slope. So we got the slope for part A to be 1, and we're pretty much there for part B also, because we wanted the equation of the tangent line, and that's just y equals mx plus b. And if the point is just 0, 0, because I got my x and y coordinate to be 0, and that's just the b value, the y-intercept is 0, so y equals 1 is the equation of the tangent line that I'm looking at through the angle pi over 4. So it kind of looks like it makes sense graphically also.